Today we're going to look at Chapter 5, the standard deviation as a ruler, and the normal model. Um, so we'll look at part of an example that involves me that I did, but I always think about, and I'm sorry for those of you who aren't into sports, but one of the things that you'll talk about in sports is if you have someone playing in one era, say of baseball, and you're going to compare them to a completely different era, you can't compare their stats directly, right? So in baseball, there was a thing called the dead ball era, which is where if you wanted to hit a home run, you needed a sledgehammer and you needed to hit it really fast, right? Today, people hit home runs, at an incredible rate compared to the dead ball era. So if you want to see who is better, you can't compare their stats directly. What we're going to look at is how can we compare their stats? Okay, and there is a way to do it. We'll get to that in just a second. Okay, the example that I'm going to use here is my SAT scores from way back in 1979. In those days, you signed up and you took it, and you didn't really know what it was other than it was important for college. And I had no idea what a good score was. Yes. This is back when it was 1600, where there were only two sections. There wasn't a writing section. It was before they did the 2400. It's also before they renormed it. It used to be the mean was 500 and the standard deviation was, for most years, was 500 and the standard deviation was about 100. Then they changed it and now it's more like 600 is closer to the mean. They made the scores all jump. Look, we did better. And I'm like, well, okay, not really, but so yeah. 800 was still the maximum. So I looked it up, and the mean score for math was 493, and the mean score for critical reading is what they called it at the time was 505. If that's all I know, and I know my scores, is that really enough to tell me if my scores were really good?
Yeah.
Well, you can see if I'm better or worse than average, right? But can you tell how much better? No. You need one more piece of information, and that's what we're going to do. The other piece of information that you would need is a standard deviation. So we use the standard deviation to standardize scores. So let me show you what I'm talking about here. To standardize a value, we subtract from the mean and then divide this difference. Actually, I should say we subtract the mean. There's no from in this. We subtract the mean and then divide this difference by the standard deviation. So if I take my score minus the mean score and then divide by the standard deviation, this is usually called a z-score. Why z? I don't know. I've never known. I guess because standardize has a z in it. Don't know. Z-scores measure the distance of a value from the mean in standard deviations. So back to my one about the dead ball era versus the current era in baseball, you could see, okay, this person is 3 standard, or let's say 2.2 standard deviations above the mean now, and you could go back to a dead ball era and say this player was only 1.8 standard deviations above the mean back then, and then you can compare those two. Oh, this player is better than that player relative to the era in which they played. Okay? And it's a pretty cool idea.
The populations are different.
Yes, the populations are different. That's the whole point. What you're comparing them to is not each other. You're comparing them to each other relative to the era in which they played. Right? So, think about it, you can do it for any athletic endeavor, right? Times in the 3,200 meter run have continued to move down. Now, it's slower than it once was, but they've continued to move down through time. So if you want to compare in, the 1920s, well, maybe this person was 2.5 standard deviations above the mean of the people who were running, and the guy now who is faster but is only 2 standard deviations above the current mean isn't as good relative to the population in which they were competing. Okay? So it allows you to compare two things, and you can actually compare completely different sports. You could do, okay, here's the mean and standard deviation for a player currently playing in the English Premier League. And you could figure out how many standard deviations they were above the mean. And you could compare that to Michael Jordan in his heyday was this many standard deviations above the mean as a scorer. And you could go, who was the better scorer? Whoever was the most standard deviations above the mean. So you can compare completely divergent things, and because you're comparing that person to the other people who were doing the same thing at the same time. That makes sense? I remember the first time I learned this, I was like, that's freaking brilliant. Because you can compare anything. How much better is this person than the average? How much better is that person than the average in a completely different arena? And then go, okay, well, comparatively, this person's better than that person at whatever it is. There's lots of good examples in your book on this. So when we standardize data, we're doing two things. First of all, we shift the data by subtracting the mean. So if we add or subtract a constant to every data point, then it's going to add or subtract the same constant to the measures of position. And you're like, measures of position. Well, that would be the minimum, quartile 1, quartile 2, quartile 3, maximum. All of those things are going to change by however much. The mean is also going to change by however much. If I give everybody a 10-point bonus, right? Well, the mean score is going to jump up 10 points. All of those things move exactly the same. Those are called measures of position. But leaves measures of spread unchanged. So measures of spread, that would be standard deviation, the interquartile range. If everyone moved up 10 points, well, the whole graph basically moved up 10 points. That doesn't change the standard deviation, and it doesn't change the interquartile range. Second, we change the spread by dividing by the standard deviation. So when we multiply or divide all the data values by any constant, all measures of position and measures of spread are multiplied or divided by that same constant. So if I multiplied everybody's grade by 3, well, that means that the interquartile range will be 3 times bigger, and the standard deviation will be 3 times bigger, and the minimum and the maximum and the quartile 1, quartile 3, median, those are all going to be 3 times bigger also. Okay? So when you multiply or divide, you move everything. When you add or subtract, you don't change the measures of spread. You just change the measures of position. So standardizing into z-scores does not change the shape of the distribution. But it does change the center by making the mean 0 and the spread by making the standard deviation 1. Shape's going to be the same. So, when is a z-score big? We'll talk more about that in a moment. But, and I sometimes wish that your book had done this as 2 separate chapters, because z-scores are one thing and the next thing we're going to talk about is actually a different thing, but you can use them both together effectively a lot of times. So, normal models. Are appropriate for distributions whose shapes are unimodal and roughly symmetric. It doesn't have to be perfectly symmetric, but roughly symmetric. A normal model provides a measure of how extreme a z-score is. There's a normal model for every combination of mean and standard deviation. The way that we'll write this as, we'll write that as capital N, and this is the mean, and this is the standard deviation. So this mean and standard deviation are part of the model. I can't stress enough, I'll try to over the next several class periods, but I won't be able to do it often enough. The model is not reality, ever. Okay? There are things that are going to be close to the normal model, but the normal model is just a mathematical way of saying, this is what we think is going on. These are, good approximations, but they're never, completely accurate. It's a model that lets us do a whole lot of other things with it. So if you try and apply a normal model to something that is not unimodal and basically symmetric, it doesn't work very well. The normal model doesn't apply. So for example, if you, have a graph that is, badly skewed to one side, like this, the normal model doesn't apply very well to that. You can get a normal model for it, it just doesn't fit very well. Okay? So anytime you have something like that, you're like, normal model's probably not good for it. You have to find some other model. And there are other models that will fit this kind of data better. We'll talk about them a long time from now. Okay? So, if we model data with a normal model and standardize them using mu and delta, that's the Greek letter mu and this is Greek letter delta. We still call the standardized score a z-score, and we will write y minus mu over delta. So normally it's easier to standardize first, then use the model in 0, 1, because we want the mean to be 0 and the standard deviation to be 1, which is called the standard normal model or the standard normal distribution. So this is what I was saying, and I wanted to say it before I even got to this point. Before trying to use the normal model, you have to check the shape of the data's distribution. If it's not unimodal and symmetric, then the normal model is not a good way to, it doesn't fit the data very well. So it's not a good model. It's not a good predictor. Okay? Check this by a histogram or a normal probability plot, which we'll get to at the very end of this particular chapter. So keep in mind that when we use a model, you're making certain assumptions. Whatever model we choose, we will always point out those assumptions and the associated conditions in the data that make those assumptions reasonable. Okay?
Mr. Davis,
Yes, ma'am.
what does a normal model look like?
That's a great question. We're going to get to that, but a normal model looks like this.
So we just kind of like stick that on like a histogram? If it,
Basically, that's what's going on, is this fits the histogram, which is part of why, if you go back to this one, well, a normal model doesn't fit that very well. If I try to fit that, it would look like this. So it's okay in here, but it way underestimates here, and it thinks there's going to be things over here that aren't even there. Okay? It's a great question.
So a normal
go-
model is like standard for everything. We just use it to compare to other data sets.
So a normal, what we do is from a histogram of our data, if that is unimodal and symmetric, then we can use a normal model for it to make predictions about things where, let's say we have the histogram, but we don't actually have all of the individual data points. We can use the normal model to predict where certain data points are going to be, or how much of the data is going to be between this point and this point. That make sense?
Yes.
So we have something that's called the rather cumbersome 68, 95, 99.7% rule. In a normal model, about 68% of the values fall within one standard deviation of the mean. About 95% of the values fall within two standard deviations of the mean, and about 99.7% of the values fall within three standard deviations of the mean. So what does that mean? It means basically there's almost nothing beyond three standard deviations. So we've talked about outliers for sets using the interquartile range. When you're using the standard deviation, if anything is 3 or more standard deviations away from the mean, that's going to be an outlier.
And how do we calculate standard deviation? Talk about that?
So yeah, for the standard deviation, most of the time you're using a calculator, but you can do it by hand by taking the difference between each data point and the mean and squaring those, and then dividing all of those added together by the number of items in your data set plus 1, and then taking the square root of the whole thing. So, I'm sorry, -1. Did I say plus? Sorry. It's the square root of the sum of all of the individual data points minus the mean squared. All over n minus 1, and then you take the square root. That's how standard deviation is calculated. So, if you're thinking about SAT scores then, if you were to score one standard deviation above the mean, so between one standard deviation below the mean and one standard deviation above the mean is 68%, that means this little part has 34%. And since the mean, when you have symmetric data like this, should be everything from here over to infinity should be 50% of your data, you're at the 84th percentile. So if you're one standard deviation above the mean, then you did better than 84% of the people. Because we've got, this is 34 plus all of this from there over is 50. That makes 84%. Okay, that's how you get what's called a percentile score. All right, tell you what, let's stop there. Normally I would go on a little bit further, but we've got people who are out and I'd like to let you guys see your quizzes. Yes, ma'am.
Why did you get the 34?
I split 68 in half.